In this video, we're going to look at the derivatives of inverse functions. And sometimes I tend to jump right into the formula or the definition theorem. In this case, I'm going to start with a little background. So I want to remember what an inverse function is. So remember, if we have a function f of x, I can write its inverse as f to the negative 1 of x. Let's write f inverse, not f to the negative 1. That's a very awkward way of saying it. It's read f inverse of x. And the idea of an inverse is that if we take a function of its inverse, or we take a inverse, clean up that inverse symbol, if we take the inverse of the function, that has to get us back to where we started, being just x. Taking a function of its inverse, or an inverse of the function, will always leave us just with the original function x. In math, we always have to have ways of undoing what we've done. So if we add 3, we know we can undo that by subtracting 3. Addition, subtraction, inverse operations. If we multiply 3, we have to be able to undo that. We can divide 3. And we have this for any number of functions. Exponentials, we have logs, vice versa. We have exponents, and we have square roots, or not just square roots, but any root, cube roots, fourth roots, whatever. We always have this way of undoing our work. So if we think about this idea of an inverse, what we are doing, what we've always said, is that we're switching the x's and the y's. So if we take a function sends x's to y's. Now, really what we're doing is we're sending domain elements to range elements. The inverse is going the opposite direction. It's sending the y's back to x's. And so whatever value I start with for the function, whenever it's taking me to the y, the inverse better be sending me back the opposite direction. Let's think about derivatives. Derivatives give us essentially a slope, more than just a slope, an instantaneous rate of change, which I've been abbreviating IRC, giving us that slope or that instantaneous rate of change a second in time. If we think about how we calculate slope, change in y over the change in x. Now with the derivative, I realize it's a little bit more fancy, right? We have the limit of the difference equation. There's a little bit more going on. But how we calculate a slope, it is a change in y over the change in x. Now when we take an instantaneous rate of change, we're looking at that change at an instant time, meaning we use that limit as x goes to, as the h goes to 0 in our difference equation. But it's the same idea. It's the change in the y over the change in the x. That's what a slope is. So if this is the slope for the function, so let me switch this notation over to slope of the function f. Well, if we know the slope of the function f, well, the slope of its inverse must be the change in x over the change in y, because what does an inverse do? It's sending those variables the opposite way around. It is simply the reciprocal of the slope of the function. To find the slope of the inverse, we would look at the reciprocal of the slope of the function. So let's make this a little bit more formal. Let's look at our first theorem, or the theorem for this section. Derivative rule for inverse functions. If f has a domain of interval I and f prime of x exists and is never 0 on I, then f inverse is differentiable at every point in its domain, the range of f. The value of this inverse function's derivative at some point b is 1 over the derivative of the inverse of the function at b. All right, so let's kind of boil this one down before we get to it. Some examples, just take it quite simply. We just said that the slope is the reciprocal of the slope of the function. Notice right here, f prime, that is saying the slope of the function. Ignore this for just a second. We have the slope of the function. If we want the slope of the inverse, we're finding its reciprocal. 1 over, that's the reciprocal. Notice I also say that the derivative, 1 has to exist, clearly, otherwise we're not going to be able to do this. But 2, it can never be 0. The reason is if it's 0, well, we have a big problem when we go to find its inverse. If the slope of the function is equal to 0 at some point, the inverse derivative would not exist at that point because we're putting the 0 into the denominator. So what's going on in here, the stuff I told you to ignore just a second ago, the f inverse of b, Well, this is how we're sending things forwards and backwards. If we're going to rely on the slope of the original function, well then we have to be talking about the x values for that original function. The b is really talking about the y value. If we're putting that b into the inverse, that's talking about the y value of the original function. So the first thing we've got to do is we've got to take that y and we've got to send it backwards to a usable form in the f. Now, let's take a look at a couple of examples, and I think hopefully this will become a little bit clearer as we go through these examples. So, given f of x is equal to the cubed root of x, we want to test the above theorem. All right, so what is this theorem really good for? Why do we need a theorem when we could just find an inverse? Well, sometimes we can't find an inverse, or it's really, really challenging to find an inverse. We just don't want to do that. And so this theorem will allow us to find those slopes for inverses we just can't or we don't want to calculate. I'm going to start with a really simple function because we can calculate the inverse of this function. And once we have the inverse, we'll be able to directly calculate its derivative. So let's start there. Let's do this one kind of the old-fashioned way without this new theorem. Let's start by finding f inverse. And so to do this, remember we switch our x's and y's, and then we solve for the new y. And so I'd take the cubed root, I'd have to cube both sides, and so I'd get y is equal to x cubed. And so this would be the inverse of our function f of x. F inverse of x is x cubed. And again, we know that roots and exponents should kind of undo each other. If I want to know the derivative of this thing, well, now that we have the function itself, we can take the derivative of x cubed. We know what that is, and that is 3x squared. So because this was a relatively simple function, we were able to easily find its inverse and then take its derivative, the old-fashioned way, right? Now let's use our new theorem. Let's apply this theorem. So one thing that I need is I'm going to have the inverse. Well, we have calculated that. We're doing it in generality for the function, which is why I've chosen a simple function. I also need the derivative of the original function. So let's get that. Let's find f prime. So the x is to the 1/3 power right now. I multiply that to the front. I have 1/3 x to the now negative 2/3 power. So that's the derivative of the function. And so let's apply our theorem. The theorem states the inverse's derivative is equal to 1 over the derivative of the function, 1/3 x to the negative 2/3. But in place of x, I'm putting the inverse function. We just calculated that inverse function a second ago to be x cubed. So I'm going to put that in my parentheses right here. 1 over the derivative evaluated at the inverse value. So we've stuck that in. Now I just have a little bit of simplification to do. So we have, I'll leave the 1/3 down there for one more second. X to the negative 2/3, well, x cubed to the negative 2/3 would simplify to x to the negative 2 because the power of 3 and the exponent of 1/3 are going to cancel each other out there. And then notice we have the 1 over 1/3 can come to the numerator as a 3, x to the negative 2 can come to the numerator as an x squared. And so the inverse function's derivative at x is exactly what we saw just a second ago. Right? We get the exact same thing. I'll just use the same notation. But we do get the same exact thing. Again, this was kind of a pointless example. We would never probably use this theorem in this case because we can easily find that inverse function. This is much more useful when we don't want to have to find the inverse function, or we just can't, right? And so let's look at another example. Find the derivative of the inverse function at x is equal to 1/7, which is equal to f of 2. I'll explain why we have that in just a minute. If f of x is equal to 1 over x cubed minus 1, where x is greater than 1. All right, so we are finding the derivative of the inverse function. That's very similar to what we were just doing a second ago. We have a function given here. Could we find the inverse of this one? Yes, but it's just not as easy as that last one, so I'd rather not, especially because they've given me all the relevant information. What I'm actually looking for is the derivative of the inverse function evaluated at an x value of 1/7. Now, this x value of 1/7, that's the inverse function's x value. That would be pertaining to the function's y value, right? So we have this idea that the x of the inverse is the y of the function. Now, I'm saying x's and y's, but really, those are just meaningless variables. The domain of the inverse is the range of the original function. And so that's why we had to be given, let me just spread this out, that's not shown up, of f. We had to be given both pieces of information, otherwise we would have had to reverse all of this. So we could have put the 1/7 over here, we would have had to have figured out what x was to give us that 1/7. But in this case, we've been given that information. All right, so I'm going to apply my theorem so I never actually have to find the inverse function. I'm going to start by just taking the derivative of f. And so if I want to find the derivative of f, in my opinion, the easiest way to do this would probably be think about the f as really being x cubed minus 1 to the negative 1 power. And so I would use my chain rule, multiply the negative 1 to the front. X cubed minus 1 is now to the negative 2 power. Then I have to multiply that by the derivative of the inner function, which is a 3x squared. And so we can simplify this a little bit as a negative 3x squared times x cubed minus 1 to the negative 2. Or if it makes you feel better, you can also put that negative 2 in the denominator. Like this, right? Doesn't matter. I'm going to stick with this line in here because I think that's just as easy. Now, we didn't just want to know the derivative of the function. We wanted to know it particularly at x is equal to 2. Now you're saying, well, wait a minute, wasn't it supposed to be 1/7? But remember, that's the x value for the inverse function. Right now, what we've done is we've switched this over to the original function. The function's x value is 2 for the inverse's x value of 1/7, or for the y value of 1/7. So what I need to do here is I need to find the derivative of the function at 2. So I'll have negative 3 times 2 squared over 2 cubed minus 1 squared. And so we will have 2 squared is 4, so negative 12 on top. On the bottom, we'd have 7 when we subtract the 1, and then 7 squared is 49. So negative 12 over 49. Now that we have negative 12 over 49, we're nearly done, because what our derivative of an inverse theorem tells us is that the derivative of the function, of the inverse function, evaluated at x is equal to 1/7, is equal to 1 over the derivative of the function evaluated at 2, which would be 1 over negative 12 over 49, which we would clean up that fraction, put the 49 back on top, we'd have a negative 49 over 12. And that would be our answer. So again, notice we never found the actual inverse here because we started with that information. We didn't have to find the inverse function. We didn't even have to calculate the y value of the inverse. We were told that, hey, when x is equal to 1/7 of the inverse function, that relates to a function position of at x is equal to 2. We calculated the derivative of the function, we plugged in that 2, and then we simply took its reciprocal to get our answer. So this can be useful when we're dealing with functions that we don't want to find their inverse function for. It can also be really useful when we are finding the derivative of functions that we haven't worked with yet. So for instance, we haven't worked with logs yet. However, we have worked with e to the x. So now that we know how to relate a function's inverse is derivative to the original function, we're going to be able to take that information, we're going to be able to use that to help us calculate the derivative of the natural log. That's where we're going with this. So you'll see that in the next video.